In this video, we're going to look at the type of speed of reaction question, which is quite common, where the question gives you different types of acids, and you are required to predict how a change in the acid affects the shape of the graph that's obtained. Now, before we go into that, a quick revision of the chapter of speed of reaction. We have earlier learned that in the context of O-levels, if we need to measure the speed of a reaction, usually the reaction will produce a gas. Okay, and when we look at reactions that produces gases, most of the time it involves the use of an acid. So acid, for example, plus reactive metals produce hydrogen gas. Acids, when they react with carbonates, they will produce carbon dioxide gas. This is why in many speed of reaction questions, we see an acid as the reactant. So in this particular example that we're going to see, we are looking at again an acid reacting with calcium carbonate, a carbonate, to produce carbon dioxide gas. So when a reaction produces a gas, we can easily monitor the speed of reaction by either measuring the volume of gas produced per unit time or the loss in mass of the reaction mixture per unit time. In this particular example, we're going to look at the volume of carbon dioxide gas produced with time. Now, if we were to measure the volume of gas produced with time and we plot a graph, the graph is going to look like what you see over here. Now, if you can recall, whenever we look at a speed of reaction graph, there are three very important points that we need to pay special attention to. One is the gradient to the tangent at the start of the reaction. This is known as the initial rate. Okay, this is the first point. The second point is the final volume of the gas produced. And the third point is the time at which the reaction is complete, or when the gradient drops to zero. Alright, so whenever we analyze the speed of reaction graph, or we try to plot a speed of reaction graph, you need to take into consideration these 3 points. So in this particular example, the acid used is hydrochloric acid, and the concentration is 1 mole per dm cube. Now, a typical question then goes on to give you two other acids, and then you are required to draw the graph that will be obtained with each acid. Another feature of such a question is that the concentration of the other acids that are given is usually the same as that for the original acid. So for this particular example, the concentration of all three acids are 1 mole per dm cube. So if you can recall, the speed of reaction depends on the concentration of the reactants, and on a superficial level it may seem that the concentration of all your reactants are the same. So shouldn't the speed of the reaction for all three acids be the same? Now the answer is no, and to know why is it no, we need to first convert the chemical equation given, which is this one, into the ionic equation. Okay, so when we convert the chemical equation into the ionic equation, it will look something like this. Now from the ionic equation, I hope you can see that after removing your spectator ions, and the spectator ions in all three cases would be the anion for your acid. Okay, so again, the anion in whichever acid that you see will be the spectator ion in this case. So the actual reactants in this reaction would be your carbonate reacting with your hydrogen ions. Your hydrogen ions is one of the main reactant in this reaction. So when we consider the concentration of your reactants, we shouldn't be looking at the concentration of the acid, but the concentration of hydrogen ions. Now look at the concentration of hydrogen ions in all three experiments where the different acids are being used. Okay, we have learned that hydrochloric acid is a strong acid. So a strong acid ionizes fully in water. So if we have 1 mole per dm cube of hydrochloric acid, essentially we are going to end up with 1 mole per dm cube of hydrogen ions. Then in experiment 2, we have ethanoic acid. Ethanoic acid is known to be a weak acid, and we have learned that weak acids only ionize partially in water. So when we have a 1 mole per dm cube concentration of ethanoic acid, essentially the amount of hydrogen ions or the concentration of hydrogen ions will be very much lower than 1 mole per dm cube. In actual fact, it is around 0.01 mole per dm cube. Now in experiment 3, we have sulfuric acid. So we have learned also that sulfuric acid is a strong acid, but the difference between sulfuric acid and hydrochloric acid is that sulfuric acid is a dibasic acid, whereas hydrochloric acid is a monobasic acid. So for a dibasic acid, 1 mole of the acid will produce 2 moles of hydrogen ions. So when we have 1 mole per dm cube of sulfuric acid, essentially the concentration of hydrogen ions will be around 2 times of the acid. Now that we have established the concentration of hydrogen ions for the 3 acids, we can then represent the initial speed of reactions in the graph by drawing in the relevant gradients. Okay, for experiment 2, since the concentration of hydrogen ions is very much lesser than experiment 1, we would expect the initial speed to be lower. We would expect the initial gradient to be less steep. So this is for experiment 2. For experiment 3, since the concentration of hydrogen ions is very much higher, so we would expect the initial speed or the initial gradient to be around 2 times or just much higher than for experiment 1. One very important point to note is that the initial speed of the reaction in this case, or in reactions that involves acids, they actually depend on the concentration of hydrogen ions. Okay, not the concentration of the acid, but the concentration of hydrogen ions. Okay, now we'll go on to look at the second important point in a speed of reaction graph, which is the final volume of CO2 gas produced, and see whether it depends on the acid that we use or not. Now, to find the total volume of CO2 produced, it is essentially a chemical calculation question, and chemical calculation questions require the use of the 3C approach. Okay, so the first C would be convert to moles. In this case, once again, the main reactant that we're looking at is your hydrogen ion. So we need to first know the number of moles of hydrogen ions. Now we are given the concentration of the acids. So let's assume, okay, in this case we have a volume of 1 dm cube to make calculations easier. The number of moles of hydrogen ions, okay, of hydrogen ions in hydrochloric acid will be 1 mole as well. Okay, the number of moles of hydrogen ions that can be obtained from ethanoic acid is also 1 mole. Okay, I know that it only ionizes partially in water, but essentially there is 1 mole of hydrogen ions that is capable of being ionized. Right, that's capable of undergoing reaction, that's capable of being ionized. Just that in water, only a small fraction of it ionizes, but there's still 1 mole of hydrogen ions present in ethanoic acid waiting to be ionized. Okay, for sulfuric acid, since again it's a dibasic acid, it will have 2 moles of hydrogen ions. Now in this example where you have excess of your carbonate, that means your acid is the limiting agent. the volume of gas produced will then depend on the number of moles of acid or the number of moles of your hydrogen ions. In this case, for experiment 2, we can see that the number of moles of hydrogen ions are the same in both experiments. So what does that mean? It means that the volume of CO2 obtained will be the same as well. Okay, so for experiment 2, the final volume of CO2 will be the same. For experiment 3, we can see that the number of moles of hydrogen ions is 2 times that of experiment 1. That means I have 2 times the number of moles of hydrogen, and therefore I will have 2 times the number of moles of carbon dioxide, and therefore I have 2 times the volume of carbon dioxide. So for experiment 3, we would expect the final volume of CO2 to be 2 times of the initial volume. Okay, now we have obtained the features for points 1 and point 2. Let's look at point number 3. Point number 3 is the time at which the reaction is complete. For experiment 2, we are producing the same volume of gas, but the speed of reaction is slower. So that means that it will take a longer time for the reaction to be complete, meaning the time at which it remains at which the gradient is 0 should be later than the original time. Okay, with that in mind, let us then complete the graph, the curve for experiment 2. Okay, this is experiment 2. How about experiment 3 then? Now experiment 3 produces 2 times the volume of gas. When the total volume of gas produced is different for the 2 experiments, we no longer care so much about the time at which the reaction is complete, because the endpoint is different. It's just like when you are running a marathon of 2 different distances, we no longer care about the timing because it's not accurate to say that the faster person will complete the marathon faster. Okay, so for experiment number 3, we no longer care about the time it completes. The important thing is that the initial gradient must be steeper and the final volume must be 2 times that of the initial volume. Okay, so I hope through this example you can see that the final volume of CO2 or the final amount of product produced does not depend on the strength of the acid, okay, but it depends on the number of moles of hydrogen ions present. Alright, why is this important is that a common mistake that students make in planning, for example, if you are asked to plan an experiment to determine the strength of an acid, some students will propose using a titration, okay, and conclude that a weaker acid will give rise to a lower titer value, whereas a stronger acid will give rise to a larger titer value. That is not correct. Okay, the titer value, which is the amount of alkali needed, is similar to the case of the amount of carbon dioxide produced. It depends on the amount or the number of moles of hydrogen ions present and not the strength of the acid. So by using titration, right, when you perform titration on a strong acid or a weak acid, if they are both monobasic, they will give the same titer value. So in a nutshell, for speed of reaction questions involving acids, the strength of the acid will affect the rate of the reaction or the speed of the reaction, because the strength of the acid will determine the concentration of hydrogen ions present in solution. The basicity of the acid will also affect the speed of the reaction, because a dibasic acid will produce 2 times the concentration of hydrogen ions as compared to a monobasic acid. As for the final volume of gas produced, the strength of the acid does not affect the final volume of gas produced or the total amount of products produced, because the total amount of products depends on the number of moles of hydrogen ions that can undergo reaction, and that is the same regardless of whether we are looking at a strong acid or weak acid. But the amount of product produced will depend on the basicity of the acid, meaning whether it's monobasic or dibasic, because for the same number of moles of a mono and a dibasic acid, the dibasic acid will produce 2 times the number of moles of hydrogen ions, which will give rise to 2 times the number of moles of products.